YoYoEngine is a 2D game engine that I've been working on solo for the past 2.5 years. It started off as just a visual novel game featuring my friends, but eventually split into its own codebase that I've used to make 2 different games, Rays of Vanny and Theriac, and a third game with the game development club that I lead at the University of Dayton called Ailurophobia. Working on this engine, it's always bothered me that on YouTube, the content related to engine development is usually either very beginner level or extremely expert level. There's not really anything in the middle to bridge the gap. If you want to learn about complex topics, your best bet is to go read articles or blog posts or source code and not actually watch YouTube videos. In this video, I'm going to talk to you at an intermediate level about how my game engine, YoYoEngine, renders scenes. First, what is a scene? Every game engine has a notion of a scene. A scene is basically a description of all of the objects in a game in a specific level. Each scene contains every piece of information about a given object and its relationship to other objects. The two most important parts of a scene are A, its data structure, which stores the objects in code, and B, the serialization of that data structure to store those objects on disk when the game isn't running. In many game engines, the data structure chosen to store objects is some sort of hierarchical tree. In YoYoEngine, I store objects using a flat list, which means they can't have hierarchical relationships with each other. The objects themselves in YoYoEngine follow the ECS paradigm, which stands for Entity Component System. ECS is a data-oriented paradigm that involves entities, which are basically empty containers, which can hold an unlimited amount of components within themselves. Components are pieces of data that describe attributes of an entity. There are components that describe position, rendering, physics. I'll talk about this when we get to the main render loop, but the systems in ECS iterate over components. That means that our rendering system only cares about entities that have a rendering component. Here's an example of what an entity looks like in code. You can see that it's basically just an empty container which holds components, with an optional name and a mandatory ID to look it up. Though this is not the traditional way of constraining components to an entity, I've decided to have a pointer to each possible component inside the entity struct itself. And to give an example of the data inside of a renderer component, you can see this following structure. A render component can either describe text, outline text, an image, an animation, or a tile map tile. Common to all of these types of renderers, you can control specific things like the texture flipping, the alignment, the transparency, and the Z level. If we're able to populate this data inside this component and attach it to a series of entities, we basically have a description of how every single object in a scene gets rendered. Importantly, however, this information needs to get populated by the developer and saved and pushed into the game. In order to let developers assign this information in the editor and then save it to the disk to be loaded later at runtime, we need to devise some sort of serialization scheme. Many other engines like Unity support different types of serialization, whether that's to YAML or to binary files. In YoYoEngine, the serialization format is JSON. Here's an example of what a renderer component looks like in the serialized JSON format. You can see that it's pretty much just a one-to-one to the structure. In YoYoEngine, I wrote all of the serialization and deserialization code myself, which is kind of a lot of boilerplate, and I would recommend maybe looking into some code gen solutions if you're interested in doing that in the future. So now that we have both our code representation of scenes and our serialization boilerplate, we have almost everything we need to start rendering them. If you'll recall, video games have quite a bit of video in them. Almost every object in a 2D game has some form of visual representation, including animations, text, and particle effects. This means that when we render our scene, we need to look at object descriptions to load things like textures. In YoYoEngine, there's a very handy method called YE_image, which will load a texture and return a pointer to it. This texture will either be pulled from the file tree when in the editor, or pulled directly from a binary pack at runtime. In order to save space and optimize reads, YoYoEngine has a custom binary asset packing format I've developed which crams the entire contents of a game's assets into one singular file. When we call YE_image, it's first going to do a cache lookup to see if we already have a stored copy of this texture from early retrieval. If we do, it'll return a reference to this existing texture, but if we don't, it'll read it from disk. This is a really important optimization because it means that if we reference the same image many times, we can greatly reduce the number of reads and memory allocations we perform. Okay, so now that we have a way to read the textures, how do we actually put them on the screen? Let me walk you through the render loop itself. At some point during every frame in the engine, we have to prepare and present a texture showing the scene as viewed by the primary active camera. This usually happens after things like physics and game-specific callbacks have been executed. The first step in this process is to retrieve the camera's details and then begin a traversal over every single entity in the ECS that has a renderer component. During this iteration, YoYoEngine will also check animation components specifically to see if we need to update their displayed frame. For render objects in YoYoEngine, there's this unique notion of bounding and alignment. Size of a render object is given by a rectangle, but the user is able to force different scaling and alignment modes onto the texture within these bounds. The first step of translating our higher level scene objects into visuals is to compute this alignment so that we can reason about the actual positions that we need to display them. After we compute the position in bounds, we do a bunch of linear algebra to compute the world position of an object, and then we transform it into the camera space. Once we've done this transformation, we can check to see if our current object actually intersects the view plane of the camera, and if it doesn't, we can discard it because it's off screen. This technique is known as occlusion culling, and it immensely improves performance by making sure that we only render objects that are actually visible to the camera. Okay, so at this point in the render pass, we've reduced our candidate objects to only the ones that should be displayed, and we've figured out the positions relative to the camera. But we still have to actually show these objects on screen. For each object, we send a buffer of its vertices into SDL render geometry, which will rasterize them and blit them onto the frame buffer. For tile map tiles and animation frames, we actually sample them out of larger atlases. So to do that, we just set the UVs that we pass to be a subset of the larger texture that it's sampling from. After sending every object into SDL render geometry and telling SDL to flip the frame buffer to the window, we have successfully rendered a single frame from our scene. Using the same generic pipeline, we can build off of it to add new functionality and handle different cases. There are also some other techniques at play in YoYoEngine like letterboxing and pillar boxing to ensure that the actual outputted frame is displayed properly on every screen resolution, but they're a little bit tedious and kind of out of scope of this video. This was just a small slice of the many processes that run inside YoYoEngine, and hopefully gave you a reasonably technical understanding of the architecture and execution of a custom engine renderer. I'm not going to pretend that this is a perfect renderer, and there's definitely many weaknesses, but I'm pretty happy with it. Not being able to actually nest entities in a hierarchical way is kind of annoying, but it's kind of a byproduct of me using this engine as a 3-year learning project. Thank you so much for watching, and I hope you've learned something.